You don't have any specific one of those memorized. Okay, any other questions from page 27? I'll take those. Okay, so do that right now. And then if you're ready to go, copy down what we're going to do. That's problem 44 from the last assignment. Or 77 it was, not 44. There was a recent discovery, and I want to tell everybody about it.
Is that actually?
What am I going to do with this? What am I going to do? And you know what? When you ask people in authority, especially politicians, are you telling the truth? Yeah, I'm telling the truth. They never are like, dang it, you got me on that one. Yep, you caught me, I'm lying. Just saying. So there's a discovery. It's crazy. It's cool.
Okay, I just wasn't sure. Like maybe you meant like test by that, like discovery, what you know. Test.
Oh, I see.
That's why I was like.
I should do that. I should turn the word test into discovery.
No, you shouldn't.
Yeah. From now on.
No, we don't know exactly. Super happy fun surprise. That
Happy fun surprise.
Yeah. Super happy fun surprise.
Give the designated checker.
Okay, we got it. Nobody gets it.
I think we're good on that one. Okay. In your notebook, this is number 77. It is the goal here was to develop the formula for the relationship between Fahrenheit and Celsius. I can never remember that. It's like 9/5 something, and then there's a 32 in there somewhere, and I never remember what to do first, second, or third. So, so let's just develop it. Okay. So the goal here is we're going to create that formula that connects those two. Okay. So how would you actually go about that? How would you go about that? Let's take known values. Good call. So general problem solving goes like this. Okay? This is a rule for, it doesn't matter where. You identify what it is that you need to figure out. Okay? And you fully understand what it is that you have to figure out. This is the problem. Do we understand what the problem is that we have to figure out? Yeah, we have to write that formula. So then next, after you've identified the problem, you identify what do you know? What are the absolutes that you know? What are the definitions? What are things that are known? And then the last thing is, how do you get from what you know to what you don't, to what you want to know? Okay? Works every time. And that's what we're going to practice all year long. Okay? Because I'm never going to give you, this is exactly how you do something. Okay? Ta-da! All right, so Fahrenheit to Celsius. Give me some values here. 32 Fahrenheit. 0 Celsius. 212. 100. That's it? We don't need any more? Turns out that the relationship is linear. Okay? So as long as we have 2 points, then we're good to go. So let's make a little graph here, and we'll see what it looks like. I always like to draw pictures. Pictures are good because it's another perspective. Okay? That's the good part. So Fahrenheit, I got to go from 0 to 212 or something. So I'm going to set 250 over here, and I'm going to go 100, 200, and then these are my 50s. So 100, 200, and then there's my 250. And then over here, Celsius only goes from 0 to 100. So we'll slap 100 up here. And of course our 0 is there. 0 on both axes, right there. All right, let's plot a couple of points. So here we go, 32, 0. So 32 would be like right here. That's 32, 0. And then 212 is 100. So that's like right here. This is 212. So that's 212, 100. Now anybody can do this, right? Could plot points. So that's what we have. And it turns out that if you connect those dots, that's the actual relationship between Fahrenheit and Celsius. Okay. Every single dot on here is a relationship. So 150 degrees Fahrenheit would correspond to whatever that one is over here. Okay. And it's for every single point. Okay, so this is the graphical view. So let's take a look at what would the algebraic view look like. How do I write the equation of this line? I can use slope-intercept, point slope. I can use any one of those that I want to. But what are the two main things that I'm actually going to need? I'm going to need to find the slope. Okay, that's key. And then I need what else? I need a point. Okay, I need a point and a slope. So let's find slope. So slope, here we go. 100 minus 0 and 212 minus 32. That's 100 and that's 180. Should I simplify that? Probably 10/18. That's 5 over 9. So that's where that 5 over 9 thing comes from. Yeah, wait a second. I thought it was supposed to be 9/5. Okay, we'll come back to that one. Thank you, Kendra. So let's see where we go. So that's a point. That's a slope, and then oh, I don't know which point to pick. Pick that one? Yeah. Is that the right one to pick? Yeah. What if I pick that one? I want to pick 76.3, and no, that would actually work, but we won't do that. So this one's easier because it's got a 0 in it. So I'm going to use the point 32, 0. And this is my recommended way. I prefer that you use point slope. So it's y minus y sub 1 is equal to m times x minus x sub 1. I prefer that you use this. You may have learned a different technique to find this, but this is what I would prefer that you do. So we plug them in. So y minus 0 is equal to 5/9 times x minus 32. Okay. And then we can clean this up a little bit. I see y is equal to 5/9 times x minus 32. I suppose I could distribute that if I wanted to. Now, I wrote x's and y's, okay? But in reality, I should have written what and what? X is the Fahrenheit. That's the independent. So the Fahrenheit is equal to 5/9. Oops, my bad. Other way around. So the Celsius, see, you guys are getting good at questioning me. C is equal to 5/9 times F minus 32. Okay? We just created the formula that if you have the Fahrenheit temperature, then you can calculate the Celsius. Okay? Does it work? Quick check. Plug in 32 for Fahrenheit. You get 0 for Celsius. Plug in a 212 here. You get a 180. 180 divided by 9 is 20 times 5 is 100. Works out perfectly. Okay? Now back to that question. I thought this was 9/5. Okay, so if we flip-flop the x's and the y's, right? So I'm going to take this right here, take this, I'm just going to peel this thing off. Whew. No, you don't, but you can watch it though.
I hate the Swivl.
Love the Swivl. So if I take this and I peel it off and I flip them, so I just actually rotated them, what I have done is I've actually pivoted these on the axis here. Okay? The y, I switched the x's and the y's. Okay? So instead of being 32, 0, it's going to be 0, 32. And instead of being 212, 100, it's going to be 100, 212. You see what I did there? So I get this new line right here. See that line? This line and that line represent the same relationships, but they are, one might say that they're inverses of each other. Well, wait a second. I remember something. Didn't in pre-calc last year you would have something like, find the inverse of this function, right? What was the very first step in finding the inverse? Switch the x and the y. Okay? We just switched the x's and the y's. Okay? And so what we did was we created the inverse, which means that if I swap these two, or what I prefer to do is I'm just going to solve for f. Okay? I'm just going to solve this equation for f. So if I take this one, I'm going to just copy it down first. 5/9 f minus 32. I'm going to solve this for f. The first thing I could do is just multiply both sides by 9/5. Right? By multiplying by 9/5, the reciprocal there turns that into 1. And so it's equal to f minus 32. And then if I add, I get 9/5 c plus 32 is equal to f. Or in other words, the Fahrenheit is equal to 9/5 times the Celsius plus the 32. And there's your other conversion. Okay? But something else also happened here. We just took a look at this inverse. Remember the 32 and the 0, they swap places? And here, the 212 and the 100, they swap places. Okay? What we really did was we drew the inverse of the function on the graph, on the same graph as the original. And you might recall something that when you graph an inverse of a function, it's a reflection over the line y equals x. Okay? A reflection over the line y equals x. So whenever you're dealing with inverses, you got to remember that you're not just finding this thing, this y equal, you're switching the y and the x. What you're actually doing is visually, you're swapping the values here, and then the graph of it is actually a reflection over the line y equals x. And we're going to work with inverse functions, inverses of functions on the AP exam, on the derivatives that we're going to calculate. Okay, we're good? Okay, function packet questions. Pull out your function packet, and I want you to look at that. Is there anything that we have not covered that is on there that when you see a quiz tomorrow on a random function that you'll be able to answer everything on it? And maybe we'll do that because I think it's so fun. We'll probably do that for a couple of days where I give you random functions that you got to just tell me everything that there is and draw me a really good graph.
Quizzes that aren't graded, or is it graded?
Well, I'm not sure yet.
Feel the love.
Yes.
Test this on a general polynomial.
Do we have what?
Test this on a general polynomial.
I could, yeah.
Would you give us like an actual equation?
I would give you, you have to be able to do the 4 different things that I talked about yesterday. Okay. All right, couple questions. Correct.
For the general polynomial one, for the domain and range, would you want us to find it for each of the situations? Or?
Great question. In the general polynomial, you can skip the domain and the range because we're not really going to fill in everything. And based upon what it is, you have a restricted range. So don't worry about that. Yeah.
The logistic function.
Oh, yeah. Yeah. What's with that? Logistic function. That one was just kind of hard, so I skipped it. All right. Jonah, what do I got? Y equals 1 over 1 plus e to the negative x? Okay.
Mr. Johnson?
Yeah.
I don't think if the projector's on, the Swivl will pick up anything.
Oh, yeah. Good call. There. Okay, lights. Okay, let me show you something kind of cool. Remember this Desmos Calculator? They actually have an app too. So I would encourage you to download that and do that because it's really cool. All right, so I'm going to say f of x is equal to 1 divided by 1 plus, 1 plus e raised to the negative x. Okay? And this is what it looks like. Now that looks kind of interesting. Okay, so let's see, why does it look like this? Give me some explanations as to why it looks like this. Give me something. I'll zoom in a little bit, but you can see, it looks as though there's asymptotes here. I wonder why there's asymptotes here. Because the further I zoom out, I see it's not getting very big here. Okay, why does it look like this?
Well, if you had 0 at the bottom, if it went to 0, it'd be undefined, but then it can't be greater than 1 because it's a fraction, 1 over something, so at least it won't reach 1. It can get close to it, but it won't ever be 1.
It can never be 1 or 0. So you're saying that it can never be 1 or 0 for the y value, right? No matter what I plug in. And why was that again?
Well, if it was 0, if you got 0 at the bottom was 0, then it would be undefined. The fraction will use 0 at the bottom, and then since it's 1 over something, it's always going to be a fraction, which will be less than 1.
Okay. What if the bottom was a half? Wouldn't it be 1 divided by a half, which is 2?
Can't be it,
Why can't it be a half?
because it's out with 1 plus something in
Okay, he's making a really good point. See this e to the negative x? That can never be negative, ever. Okay? It can be a really big number or it can be a really small number, but it cannot be anything negative. So I'm always going to be adding on 1 plus something that's positive. Okay, either big number or small number. So get a couple points. If I let x equal 0, what do you get for the answer? E to the 0 is 1. So it's 1/2 for our answer. And that's where this guy, of course, is right here. Okay? And you can find the other places by plugging in numbers. If you go out to 1, this is going to be, if I go to 1, just think of it as I'm looking at 1 over 1 plus e to the negative 1, which is 1 over e. Okay? Now, for our purposes, if we're calculating this and we're just doing it numerically without a calculator, what's 1 over e about? It's around 1/3, right? Because it's like 2.7. So this is about 1/3. So this is 1 over 1 plus 1/3. What's 1 plus 1/3? 4/3. And so I got 1 divided by 4/3, which is, it's going to be roughly 3/4, and that's why the 3/4 is right about there. Okay, you can do this, just mental math, that, and the same thing for the other side. So we can start to fill these in, and you can get those values. This being 1 on top, and at the bottom, never being 0. Okay, never being anything less than 1 means that we can't possibly, we're restricted on the numbers that come out. If this turns into a really, really, really big number, look at what happens. If I start plugging in like -3, -4, -100, -10,000, what's going to happen here if I plug in, let me just do a -10. -10 plugged in is 1 over 1 plus e to the -10, which is e to the 10th. Okay? E to the 10th, that's a pretty big number. If I add 1 to it, and then I make a fraction out of this, this makes a really small number. Okay, point something. Which is why the asymptote here, as you go to the left, we say it as x is approaching negative infinity, is going to, the y value is going to get closer and closer to 0. Okay? If we go the other way, if we plug in a positive 10, this is going to be 1 plus 1 over e to the 10th like this. And that means that this number is going to become, this part right here is 1 divided by e to the 10th. That's our really small number. And so what's going to happen is this is going to get really, really, really close to 1 as a final answer. And that's why the asymptote is right here. Okay? So if you take a close look at it, this is what you get. Now I want to show you some fun stuff. There's these things called sliders in here. So I'm going to change this to A. Okay, and I'm gonna let it play. Now, do you see what's going on here? If I pause it, I'll just pause it, say like right here. Okay, so A is 5. That's where the top of it goes. See, that's where the asymptote is. So we can modify it in that way, just like we can modify all the other functions, you know, to be that. I can put in another one here. And I'll pause this one and I'll play this one. I have to zoom in on this one. Look at what it does to this. Okay, so this is what B does. If I change that number right here, this is how it changes it, which is kind of funky. And then it's fun when you do both of them. pause them and put them at different spots. And then it's kind of fun. What we're drawing is, we have the ability, it's like on your graphing calculator, where you only have like 8 possible functions. Here we have drawn 1,000 different functions, like one right after the other, because it's an animation where A is changing and B is changing. And then I can change this one too. And let's go nuts on this. So what it's doing, you can see here, it's changing the shift. So I'm going to pause that one for a second and then have it pick up. Here. So each of these, I got 3 different variables going on at different times, modifying it. And this is how people explore to try to understand how the graphs go. Imagine Newton having this. Or Descartes. You know, he did everything with really, really, really bad paper and pencils. And he didn't even have pencils. Ink pens. Okay, so anyway, this is the function. And it's the slider concept, and it's really, really powerful. So, okay, any other questions from the function packet? Yeah.
So good if there's nothing else to answer, like all the domain or the
Yes. Everything except for the bounded. I don't really care about that.
Pass failings.
We good? Okay, just a quick question. What is a piecewise function? One person. Anybody? Gunnar, what do you got?
A bunch of functions put together in some way.
A bunch of functions put together in some way. Okay, somebody add to that? What does that mean? Yes. Okay, I like that, where one function starts and where another one ends. Each of the functions has their own domain. I like that. Okay, what else? It's kind of that's pretty good. There's a way that we can do this. Oopsie. I'm going to have to recall how that goes again. You can easily do piecewise functions on here, but I have to recall it in order to do it, so I'm not going to show you today. All right, anything else? Yes. Just in general, the one that you got there? Okay. Let's do lights. So obviously there's lots of different, there's an infinite number of solutions to this, to the different types of piecewise functions that you can have. This one says this, x plus 4 for when x is less than -1, and then it's y equals x squared for when x is between -1 and 2, and then it's 4 when x is greater than 2. Okay, so this is the big picture here. So what you got to do is you got to find your lanes. So in this case, -1 is a lane because I spy it here, and then 2 is a lane as well here. And so you kind of think of it like this. I'm going to split this thing into those three sections, door number 1, door number 2, and door number 3. Okay, so I'm going to draw this one, y equals x plus 4, only when x is less than negative 1. So I'm going to go 1, 2, 3, 4. I know how to graph that. It's got a y-intercept of 4, and then it's got a slope of 1. So the way that I could do it, I could plot here, and then go down 1, back 1, down 1, back 1. Oops. The way my graph is, I got to go like this. Down 1, back 1, and so on. Okay? Now, I could draw this whole line right here. That's the line y equals x plus 4. But I'm only allowed to draw it. This is my restriction when x is less than negative 1. So I got to put an open circle here, and I graph this one. Does that ring a bell? Okay. Then you do the same thing for each one. You draw the full graph, and then you just erase it where it doesn't belong. Okay, hey, I got to show you something. This just came across the wire. I don't know if you guys stay up on current news, but I saw this today. I don't know, it blew my mind, so maybe you figure it out. So follow me on this proof. If I let A equal B, I can multiply both sides by the A because we have this multiplication property of equality. You can multiply equal things by equal things, and the answers are equal. So I can multiply this side by A and this side by A. So that gives me that A squared is equal to AB. Right? Just make sure you're checking my algebra here. Then we have the subtraction property of equality, so I can subtract equal things from equal things, and the results are equal. So if I take this left side and I subtract b squared, and I take the right side and I subtract b squared, I get this. There's nothing wrong with subtracting equal things from equal things. Then we can actually factor a squared minus b squared. I remember that one. What is that? A minus b times a plus b. Remember that from last year? So a squared minus b squared is a minus b times a plus b. And then over here, actually, there's a b that's common. So I can factor out the b, and I get that. Okay. And then look at, there's an a minus b on both sides, so I can cancel those. And that leaves me with a plus b is equal to b. But then since a and b are equal, I can replace it. B plus b, which means that 2b is equal to b, and I could just divide both sides by b, and therefore 2 is equal to 1. All right, we'll talk about this tomorrow. It's changing our world.